Hello, this time we're going to take into the topic of partial sums and polynomial fitting. So for this, I'd like you to consider this example of a sequence, and we would like to find a formula for it, one that fits the terms of the sequence. So let us find a formula. You may say, how? How can we proceed? Well, I'm going to make first a little table that contains information about the sequence itself, the position, the term, and their differences. So I'll start like this. Start by checking the differences or the difference of consecutive terms. Roughly, we need to create something that looks like this, and I have Sn, and I'm going to have S of n minus S of n minus 1. Of course, this is only applicable after the initial value. So we start, well, for 0, as indicated here, this is 3, and this one, well, that one is undefined. For 1, this is 5, and the difference is 2. For 2, the term is 9, and the difference is 4. For 3, it's 15, the difference is 6. For 4, the position, the term is 23, and the difference is 8. So now, something that we have to notice is that the differences follow an arithmetic sequence. And we're going to take advantage of that, because now we're going to rewrite the terms of the original sequence using these components. So let's proceed. Use this data to rewrite. So now, the sequence itself may be written in this fashion: 3, comma, 3 plus 2, then 3 plus 2 plus 4, then 3 plus 2 plus 4 plus 6, then 3 plus 2 plus 4 plus 6 plus 8. Then we see, well, look, this is my 5, this is 9, this is 15, and, well, this is 23. It's just another way of writing them. And we identify now a pattern, right, in this sequence. So I have S, of course, and then I have a 3. I have 3 plus 2 times 1, if you want to say it in that way. Then 3 plus 2 times 1 plus 2. Then 3 plus 2 times 1 plus 2 plus 3. Then 3 plus 2 times 1 plus 2 plus 3 plus 4. Right? Now, we look at the positions, right, associated with this. This is position 0, this is position 1, 2, 3, and 4. So that tells me that I may write the term of the sequence in the following way, right? So for each n greater or equal than 0, of course, natural number, we would say that S of n is equal to 3 plus 2 times the sum ranging from 1 up to n of this dummy variable k. And well, we wonder if there's anything that we can do with this expression that we have. And yes, of course, something that we have to recall is that sums that have this format, right, running in this fashion, a sum of this kind is equal to n times n plus 1 divided by 2. You may use the Gauss trick in order to provide it. But in this case, this says that this is 3 plus 2 times n plus 1 divided by 2. You may also simplify it to n squared plus n plus 3. Which turns out to be a quadratic polynomial in n. But then, if we take a look at this and say, well, is there anything special about a quadratic polynomial appearing in this type of sequence where the differences that we have here, right, these differences here, form an arithmetic sequence? Well, it turns out to be that that has not to be the case, as we're going to demonstrate shortly. Right? Let me just move a little bit forward. And I would say, okay, what if I have, to begin with, a sequence of this kind? So let us now start with something that has this format, a sequence where a polynomial is prescribed with a different from 0, b and c, just numbers. They could be rational, real, complex, doesn't matter. And then we examine, right? Let's examine the form of consecutive differences. Once we do that, we have this. We have an squared plus bn plus c minus 2 minus a times n minus 1 squared minus b times n minus 1 minus c. Of course, after some computation, this reduces to 2na plus b. Now we see that this new sequence, right, that we're defining is indeed, well, given by a linear polynomial, which is exactly the form of those arithmetic sequences. So, what is this saying, right? If I were to take let me write it here to keep it in mind. If I were to take the differences of this, well, now it will turn out to be a constant sequence. In other words, if I start with a quadratic polynomial, then I take consecutive differences. That produces a new sequence. But if I were to take the consecutive differences of that new sequence, meaning the second order differences, that would be a constant. Produce a constant sequence. In fact, this is what characterizes sequences given by a polynomial of degree k. If you were to take the kth order differences of that sequence, well, the resulting sequence would be a constant. This reminds me of taking derivatives. When you have, let's say, a polynomial of degree 3, and you take the third order derivative, you get a constant. When you have a quadratic polynomial and you take the second order derivative of that polynomial, well, you get a constant. So this gives this. I want to end up this discussion with the following question: if you encounter a sequence where the third order differences is constant, meaning it's a constant sequence, can you fit the original sequence with a polynomial? If so, of what order? And I'd like to finish with this. Take care.